The sky over the northern hemisphere stopped being predictable sometime around the first weeks of April 2026. Not gradually, not subtly. It changed the way a window changes when something hits it, all at once, with force and with consequences that don't stop radiating outward. The American Meteor Society's external data streams have now established a baseline that is impossible to explain away. Fireball events confirmed by more than 50 independent witnesses have doubled compared to the rigorous 5-year historical average, 100% increase. And if you've been watching the tracking feeds, you already know these are not the familiar ghostly streaks of the Perseids fading out somewhere above the stratosphere. These are objects that drive down through the atmosphere with enough mass and momentum to cast hard shadows on the ground. They terminate in concussive sonic booms that rattle seismometer arrays and leave behind tangible, anomalous mineral deposits across populated landscapes. Every single one of these amplified events is originating from the same direction, the Anthelion radiant, the precise point in the sky sitting directly opposite the sun. Before we go any further, if you're not already subscribed to this channel, now is the moment. This situation is evolving in real time, and the analysis here will track every significant development as it emerges. Now, the Anthelion geometry matters enormously, and it's worth pausing here because the kinematic implications of that single directional fact are the skeleton key to understanding everything that follows. Objects arriving from the Anthelion radiant are not hitting Earth head-on. They are coming up from behind, overtaking our planet in low eccentricity orbits that closely mirror Earth's own path. Because of this trailing edge approach, their velocity relative to our upper atmosphere is slashed down to somewhere between 11 and 15 kilometers per second. To put that in physical terms, a retrograde meteor is a head-on collision on a motorway at combined closing speeds that would obliterate both vehicles instantaneously. An Anthelion fireball is a gentle rear end from a vehicle traveling in the same lane, at nearly the same speed. The thermal penalty for entering the atmosphere at that reduced velocity is dramatically lower. Less kinetic energy means less heat. Less heat means the objects survive deeper into the atmosphere before the thermal assault overcomes them. That's why we're getting sonic booms. That's why they're hitting the ground. Here's the thing, though. This mechanical explanation is clean and satisfying right up until the moment you look at the full flux data set. And that's where the clean explanation falls apart completely. The atmospheric sensor networks and the space-based infrared early warning satellites confirm something that should not be possible. The total overall meteoroid flux, the raw, absolute mass of debris entering the atmosphere, has not moved. The background volume of cosmic dust and micrometeorites is perfectly stable, tracking exactly where it should be according to decades of historical data. What has changed, violently and without any gradual transition, is the size distribution within that flux. The microscopic dust is gone, mathematically vanished from the mass balance equation, and in its place, filling that mass budget entirely, are dense, large fragments of asteroid origin. Something has surgically removed the smallest particles and replaced them with boulders. That is not a natural drift. That is a structural change to the population of objects reaching us, and it happened essentially overnight. And then the recovered surface deposits make everything worse. The chemical assays of the stones coming down are producing a result that has forced independent analysts to go back and recheck their instrumentation multiple times. The recovered stones are pristinely unshocked. Their crystal lattices show no evidence of violent impact heating in space. None. Yet their outer layers carry an isotopic signature that definitively proves they were encased in dense, volatile ice until mere months before atmospheric entry. Those two facts should not coexist in the same object. Asteroids from the inner solar system don't carry volatile ice shields. Comets from the outer solar system don't have unshocked, massive rocky cores devoid of microscopic dust. Whatever these things are, they don't fit any established category. Let's talk about the radar data, because it introduces yet another layer that the standard models cannot absorb. When a normal meteoroid falls through Earth's gravitational sphere of influence, it accelerates smoothly down the gravity well. It compresses the air ahead of it through adiabatic compression, generates a plasma sheath exceeding 10,000 degrees Kelvin, and ablates in a predictable, smooth curve that phased array radar systems can track cleanly. The deceleration profile is a readable, well-understood signature. The radar cross-section changes smoothly as the object sheds mass. The Anthelion fireballs of 2026 are not doing that. The raw phased array data shows these objects shedding immense transient layers of material that flash freeze in the extreme cold of the mesosphere before burning, creating secondary radar returns that briefly mimic a surrounding swarm of smaller objects. The deceleration curves are fluctuating in a way that implies the internal density of these objects is actively changing during descent. That is not a property of solid rock. Wait, it gets weirder. The infrasound arrays, the networks built to monitor nuclear test ban treaties, are recording the Mach cones generated by these objects, and the acoustic signature is uniquely and unmistakably ragged. A solid iron or stony asteroid produces a clean, sharp N-wave profile. The 2026 Anthelion objects are producing a sustained, chaotic roar. That acoustic data maps directly onto what you'd expect if high-pressure gas was escaping through the object during flight, violently disrupting the smooth aerodynamic flow and tearing the Mach cone into turbulence. Something inside these objects is outgassing aggressively, and that escaping gas is almost certainly acting as a thermal buffer, a cooling envelope temporarily shielding the primary mass from the full heat of the plasma sheath, buying it extra survival time as it punches deeper into the atmosphere. But then the atmospheric LIDAR networks return a result that stops everything dead. The trails left behind by these fireballs contain absolutely zero trace of water vapor, none. If the volatile substance doing all of this work, shielding the rocks, enabling the deep penetration, creating the ragged acoustics, is not water ice, then the entire compositional framework for understanding objects like this needs to be rebuilt from the foundation. The spectrographic data from independent observatories is unambiguous. As these objects burn, the emission spectrum should, if water ice is present, show strong hydrogen and oxygen lines. Instead, the spectrometers are being saturated by intense sodium doublets and heavy signatures of frozen carbon dioxide. And alongside those, carbon monoxide, solid carbon monoxide ice. That substance sublimates at temperatures barely above absolute zero. It cannot exist in any region of the solar system warm enough to be relevant to inner solar system dynamics. For carbon monoxide ice to still be present on these objects, they must have originated in and remained within the deepest, coldest regions of the outer solar system, well beyond the orbit of Neptune, until recently. Very recently. Here's the kinematic paradox that creates. An object falling inward from the Kuiper belt or the Oort cloud accumulates gravitational potential energy the entire way down. By the time it crosses Earth's orbit, it's moving fast. Think about Comet Swift-Tuttle's debris. Those particles hit the atmosphere at 60 kilometers per second. Yet these objects are arriving at 11 kilometers per second in flat, near-circular orbits indistinguishable from ordinary main belt asteroids. How does something born in the outer solar system shed 90% of its orbital velocity and perfectly circularize its path without ever coming close enough to the Sun to destroy its carbon monoxide ice coating? I want to hear what you think is driving this. Drop your analysis in the comments. Are you leaning toward a resonance cascade, an external perturbation, or something else entirely? 3 hypotheses have emerged from the community of celestial mechanicians currently working this problem. Let's run each one against the hard telemetry and see what survives. The first is the distant gravitational resonance theory. The Kozai-Lidov mechanism explains how a massive, distant, perturbing body, the theoretical Planet 9, could, over millions of years, gradually pump the eccentricity of Kuiper belt objects, sending them diving inward. As they cross Jupiter's domain, a Tisserand encounter could theoretically drain their kinetic energy, circularizing the orbit and eventually delivering them to near-Earth space at low relative velocity. It's an elegant chain of events that handles the velocity problem neatly. It doesn't survive contact with the tracking data. Gravitational scattering by Jupiter is chaotic by nature. It distributes objects across a wide range of inclinations and eccentricities. Every single massive boulder tracked by the phased array radar network in this swarm shares an identical orbital inclination, 4.83 degrees off the ecliptic plane. Their argument of periapsis, the angle of closest solar approach, is also identically aligned. This is not a randomly scattered population. This is a cohesive, tightly bound orbital stream moving in absolute unison. And when the trajectories are run backward in time using supercomputer orbital integration, not one of them has passed anywhere near Jupiter in the last 10,000 years. The Jupiter scattering hypothesis is eliminated. The second hypothesis is interstellar stream interaction. The solar system is currently moving through the local interstellar cloud, and that cloud is not uniform in density. If we recently crossed a high-density filament, the compressed heliosphere boundary would allow neutral interstellar gas to penetrate deep into the inner solar system. That incoming gas would create a sudden headwind in the asteroid belt. Gas drag operating on microscopic particles would be devastating. Small, light dust grains would be blown out of their orbits, either driven into the Sun or scattered out of the ecliptic entirely. This cleanly explains the disappearance of the microscopic dust from the flux data. But look at what it cannot explain. A dense boulder has far too much momentum to be deflected by the microscopic friction of tenuous neutral hydrogen atoms. The gas stream hypothesis has no mechanism for delivering massive objects. And even if we extend the model to argue that the dust headwind sandblasted larger asteroids and exposed fresh material, that process would leave unmistakable micro-cratering and shock metamorphic signatures across the crystal lattice of the recovered minerals. The electron microscope imagery of the Anthelion meteorites shows flawless olivine and pyroxene crystals, not a single shock lamella. The interstellar stream hypothesis fails the physical mechanics test. It's analytically finished. The third hypothesis is a lingering echo of an ancient Kuiper belt collision. Collisional cascades are real and well understood. Two icy dwarf planets colliding head-on could shatter their outer layers while leaving deep internal core fragments relatively unshocked. The Yarkovsky effect, the slow orbital drift caused by asymmetric thermal radiation from a rotating body, could theoretically nudge these fragments into Earth-crossing trajectories over geological time. The timeline destroys it. The Yarkovsky effect is measured in millions of years of gradual nudging. The AMS data is unequivocal. In December 2025, Anthelion flux was entirely normal. By April 2026, it had doubled and shifted overwhelmingly toward massive objects. A slow, continuous thermal force cannot produce a sudden, discrete spike in Earth-intersecting trajectories. And the isotopic analysis drives the final nail. Mass spectrometry analyzing the decay ratios of aluminum-26 and iron-60 provides a precise formation clock. The oxygen isotope ratios, specifically the ratio of oxygen-16 to oxygen-17, do not match primordial Kuiper belt material. They lock these rocks to the outer main asteroid belt between 2.5 and 3.2 astronomical units from the Sun. These objects were not born in the deep outer solar system. They formed right in our neighborhood. Yet they're coated in carbon monoxide ice that cannot survive anywhere near their stated origin. The Kuiper belt collision hypothesis collapses under the weight of its own isotopic data. Every single hypothesis fails, individually, and that's the key insight, because the solution to the Anthelion Shift of 2026 cannot be found in any single phenomenon. It requires exactly 3 simultaneous, highly specific physical events interacting in a precise sequence. Start with the source. Deep within the outer main asteroid belt exists a class of objects known as dark families, heavily weathered, ancient asteroids built from porous, unshocked carbonaceous chondrite material. They have occupied stable orbits for billions of years, accumulating thick surface layers of microscopic dust. The radar tracking data's specific inclination node of 4.83 degrees points directly to a known but obscure dark family located precisely on the inner edge of the 3-to-1 mean motion resonance with Jupiter. That resonance is a gravitational cliff edge. Objects parked safely away from it are stable indefinitely. But if an object is nudged even slightly across that boundary, Jupiter's immense gravity seizes it immediately, rapidly inflating its orbital eccentricity and hurling it toward the inner solar system on a timescale measured in months. Not millions of years, months. That single mechanism explains both the sudden onset and the precise, uniform orbital alignment of the incoming stream. Now, what provided the nudge? The asteroids in this dark family are too massive to be moved by solar wind pressure. The Yarkovsky effect is too slow. The nudge had to be physical, a collision. But the meteorites are unshocked. That contradiction is not a problem. It is the fingerprint of a very specific type of impactor. Think about what happens if the impactor was not another rocky asteroid, but a fragment of a long-period comet falling in from the Oort cloud. A comet is a loosely bound matrix of hypervolatile ice, including carbon monoxide and dust. When that fragment strikes a highly porous asteroid, the impact dynamics are completely unlike a rock-on-rock collision. The kinetic energy of the impact instantly vaporizes the comet's volatile inventory. That rapid vaporization produces an explosive expansion of hyper-chilled gas. The shock wave propagates through the porous asteroid rock in a process called spallation. The compressive wave travels through the body and reflects off the far side as a tensile wave. Rock resists compression readily. It is catastrophically weak under tension. The far side of the asteroid peels away in massive, pristine, unshocked slabs, intact crystal structures, no shock lamellae, exactly what the electron microscope imagery shows. That single collision event solves nearly every variable at once. The spallation fractures the asteroid into massive, unshocked boulders. The explosive carbon monoxide vaporization surrounds those newly freed boulders in a hyper-chilled, rapidly expanding gas cloud. In the near vacuum of space, that gas immediately undergoes reverse sublimation, refreezing as a pristine layer of solid carbon monoxide ice encasing the rocky fragments, exactly the coating the atmospheric spectroscopy detected. The kinetic energy transferred by the spallation event imparts just enough velocity change to push these newly ice-coated boulders fractionally across the gravitational boundary into the 3-to-1 mean motion resonance. Jupiter's gravity does the rest, stretching their orbits and sending them diving toward Earth's orbital path within months. Because they're coming from a main belt resonance rather than falling from the deep outer solar system, their arrival geometry matches precisely the slow, trailing edge Anthelion vectors the AMS has been recording. One last piece. Where did the collision dust go? A shattered asteroid should produce millions of tons of microscopic fragments alongside the boulders. The LIDAR networks and flux data show no such dust arrived at Earth. Here's what happened to it. When the comet struck and the carbon monoxide detonated, the expanding gas cloud acted as a violent, localized dispersal wind. The massive boulders had enough inertia to resist it, falling into the Jupiter resonance. The microscopic dust from both the comet and the asteroid's surface layers was entrained in that expanding cloud and accelerated outward. Once dispersed over a vast area at roughly 3.2 astronomical units, those individual dust grains were exposed directly to solar radiation pressure. At that distance, radiation pressure is the dominant force acting on micrometer-scale particles. It pushed them outward, away from the Sun, away from the resonance gap, and away from Earth. The solar system performed an automatic mass sorting operation. Jupiter's gravity pulled the boulders inward. Solar radiation pressure blew the dust outward. Earth received the boulders and none of the dust. The flux equation balances perfectly. If this analysis has helped clarify what's unfolding, please hit the like button. It genuinely helps this kind of detailed scientific content reach a wider audience. So, the Anthelion Shift of 2026 is not a Planet 9 resonance cascade. It's not an interstellar cloud passage. It's not an ancient Kuiper belt echo. It is the immediate cascading fallout of one specific, low-probability impact event in the outer main asteroid belt. A comet fragment from the Oort cloud struck a porous dark family asteroid sitting precisely on the gravitational edge of the 3-to-1 Jupiter resonance. The spallation fractured it into massive unshocked boulders. The volatile detonation coated them in carbon monoxide ice and scattered the dust away from the sun, and Jupiter's gravity funneled the boulder stream directly into Earth-crossing trajectories within months. Every data point, the oxygen isotopes, the acoustic profiles, the radar deceleration curves, the missing dust, the carbon monoxide spectroscopy, the flawless crystal structures, slots into that sequence without contradiction. The resolution of that orbital puzzle, however, immediately surfaces something operationally urgent. The optical camera networks recording these events are passive, sky-dependent, nighttime instruments. They record detonations after they happen. To map and monitor an active, cohesive orbital swarm like this one in real time, passive observation is not sufficient. Phased array radar systems, electronically steered networks using thousands of stationary antennas that can sweep synthetic beams across the entire sky thousands of times per second, need to replace the mechanically steered parabolic dish infrastructure that still forms the backbone of most ground-based tracking. The proposed upgrades to the Goldstone Deep Space Communications Complex and the planned replacements for the Arecibo architecture represent exactly the right technical direction. Add to that the integration of synthetic aperture radar techniques into orbital early warning satellites, and we begin to develop the capability to detect this incoming swarm long before individual objects reach the atmosphere. Because the baseline assumption that has governed near-Earth space monitoring, that the asteroid belt is a slowly, steadily leaking reservoir, has been empirically broken by what happened in April 2026. The inner solar system is not a clockwork. It is a dynamically coupled, chaotically balanced environment where a single collision 300 million miles away can propagate through gravitational resonances and deliver a doubled fireball rate to our atmosphere within months. Continuously mapping the dark families perched on the edges of those resonance zones in real time with active radar rather than passive optical instruments is no longer an academic priority. It is a planetary defense requirement. The unshocked ice-coated stones still being recovered from surface deposits are not curiosities. They are physical records, perfectly preserved hard drives encoding the granular telemetry of a catastrophic collision event, delivered here by the immense, indifferent mechanics of the solar system. The puzzle of their origin is solved, but the Doppler shift tracking data streaming from the phased array networks right now is revealing something that demands immediate attention. The spatial density of the remaining objects, still within the 3-to-1 Jupiter resonance gap, is not decaying the way the orbital dynamic models predict it should. It is tightening. The orbital node is compressing. That pattern doesn't match the gradual dispersal of a single fragmentation event. It matches the signature of a parent body that wasn't simply cracked on its outer surface by the initial spallation, but one whose entire internal structural integrity was critically and irreversibly compromised. If the core of that dark family asteroid is currently undergoing a delayed, cascading internal fragmentation deep inside the resonance gap, then what the AMS recorded in the first quarter of 2026 is not the peak of the Anthelion Shift. It is the opening signal. The denser part of the stream hasn't arrived yet.